And today we're going to have Andy, and Andy's going to talk about Hamiltonian operators and free fermionic lattice models. Thank you for coming.
Hi, everybody. Thanks so much to the organizers for having me. I'm really excited. I love this seminar, so I'm excited to get to speak. So I'm going to talk about a few things, some of which is perhaps new, but we're kind of like trying to see what everybody thinks as well, because it's possible that some of this could be kind of in the literature from very long ago. So when we get to that point, I'll kind of see if people have any thoughts or know of anything. But I'm also going to go through some stuff, in particular, a paper by Thomas Lamb called A Combinatorial Generalization of the Boson Fermion Correspondence is kind of key to what we're going to talk about here. And then two papers by members of the audience, one by Brubaker and Schultz, talked about Hamiltonians for the Six Vertex Model, and a more recent one by Brubaker, Buciumas, Bump, and Gustafsson talked about Hamiltonian operators for Q-Fock space. And so if you were at the seminar a few weeks ago, Dan Bump gave a really excellent talk about Hamiltonian operators. I'm going to repeat some of the stuff here, and some of it I'll kind of direct you back to his notes. So our goal, as we're approaching it now, is to sort of use Hamiltonian operators to prove identities about symmetric functions. And the idea is that we have lots of good identities about Schur functions, and so Hamiltonians, in a sense, allow us to generalize the concept of a Schur function to other symmetric functions and allow us to do similar operations that we could do for Schur functions. So in that spirit, if we can do several different kind of important Schur function identities on the Hamiltonian side. So for instance, a Cauchy identity, if interpreted right, can be seen as a commutation relation for Hamiltonians. A Pieri identity is the action of a certain operator, which we'll mention later. Jacobi-Trudy formula, it only applies, as far as I can tell, for Hamiltonians connected to Fock space, but essentially the Jacobi-Trudy formula, the Hamiltonian analog is called Wick's theorem. And I'm not really going to talk about branching rule, but I just wanted to mention that Hamiltonians do have branching rules, and they're adjoint to the Pieri rule. So when we have Hamiltonians, we get lots of nice identities, and so that's one reason that we like them. And so later on, we're going to talk about which lattice models have Hamiltonians and ongoing work there, and try to prove identities and facts about them. So first, we're going to talk about Heisenberg algebras a little bit. So a Heisenberg algebra, we're going to call this mathcal H. It's generated by these generators B sub k's for all non-zero integers, such that they commute unless k and l are negatives of each other, and then it's just a factor of k. And one important fact about these that you can see in Lamb's paper, or even better in Katz and Reina's Bombay lectures, is there's a uniqueness of representations. So basically, if you have two representations of a Heisenberg algebra and they're not trivial in some way, there's a unique isomorphism of Heisenberg algebra modules that map the highest weight vector from one to the other. And the highest weight vector is sort of so that if we think of the positive BKs as kind of raising operators, that if you apply those, then it kills the vector. So there's a concept of highest weight vectors, and we have unique representations up to the highest weight vector. So everything is in the realization of the representation here. There's no kind of representation theory going on, because it's all the same representation that we're dealing with. And so we're going to talk about two important, obviously, isomorphic representations, and the fact that they're isomorphic is the reason that we can do things. So the first one is the bosonic Fock space, where our vector space is the algebra of symmetric functions. And the action of the generators is either multiplication by a power sum polynomial, or differentiation by that power sum polynomial. So based on applying different base of k's, we can build up a polynomial in this bosonic Fock space. And if we do it in an interesting way, we'll get an interesting polynomial. So again, throughout the talk, p sub k is just going to be the power sum symmetric function. And a lot of what we're doing here is essentially changing this to some other function and seeing what happens. And so in this case, the highest weight vector is just the polynomial 1. And like I just said, it's a little bit technical, but if we're willing to scale the generators, we can just, instead of the power sum symmetric functions, we can replace them with other algebraically independent sets of symmetric functions. And so we're going to sort of slightly generalize how this bosonic thing works, but because we can scale the generators, it's nothing to really worry about too much. So then on the other hand, we have the fermionic Fock space, and this is the regular one, not the Q-deformed Fock space. And so this comes from a Clifford algebra structure. We have operators psi I star and psi I. We call these creation operators and these deletion operators. And you'll see in a moment kind of why we're calling them that. And so there are three basic relations, which is that essentially, for the most part, they anti-commute. So if we do psi I psi j, that's equal to negative psi j psi I. And that's the same for creation operators. They anti-commute. And for a deletion and a creation operator, they also anti-commute, except in the case where I equals j, and then they don't quite anti-commute. And so these are going to act on fermionic Fock space and its dual. So essentially, this is the space of free fermions. We just have all the possible psi I stars and all the possible psi I's. And then we have these two different representations coming from essentially having all particles on one side and all holes on the other, and vice versa. So when we mod out by these two subspaces, we get a left A module here and a right A module here. And these are kind of our Fock space and our dual Fock space. And so these modules are both cyclic, and their generators we're going to call this ket 0 for F and the bra 0 for F star. And so we're going to pair these together with a particular bilinear pairing coming from what's called the vacuum expectation state. I should mention another source, which is Jimbo and Miwa's solitons paper. It's like a 60-page paper. It's got a lot of this stuff as well. Really good exposition. So how do we actually think about these things? We usually don't think about them in terms of just all these symbols on a page. We think of them in terms of states of particles. So this is called the Dirac sea. And so each basis vector is a state of particles. So this vacuum vector, this generator, is the vector where I say that to the left of 0, so this is to the minus side, we have all particles. To the right of 0, we have all holes. And if I do a creation or deletion operator, I can create particles or delete particles. So if I want to create one at 3/2, I just do that, right? This is 0, so this is 1/2, and this is 3/2. And so I've now created a particle here. And if I want to delete a particle, say I want to delete it at -1/2, I just delete that there. And so this is the way that we typically, like when you're visualizing these operators in your head, you should visualize it as acting on the Dirac sea. So then there is a kind of a copy of GL infinity, where we have all of what are called the group-like elements. So I'm not going to go through exactly what the normal ordering is. It's a way to get rid of like accidentally getting infinity when you don't want infinity. or not accidentally, but it gets rid of infinite quantities that don't really mean anything. But basically, GL infinity is the sum of all these, like all linear combinations of pairs of creation and deletion. So it's really important that they're pairs of creation and deletion, because what it means is, to some extent, particles aren't created or deleted, they're just moved. And maybe we kill the space, but if we don't kill the space, it's going to have the same number of particles. Well, it's going to have infinitely many particles, but if you pick a certain spot, it's going to kind of have the same number of, or how should I say this? If you count the particles from the right, you will eventually kind of converge to a certain number of particles based on how many spots you've gone below 0 in. So this preserves that. And so we don't say that these sums have to be finite, but we do say that the I and j have to be close together. They can't be arbitrarily far apart in any of these elements. And so with all of this, F decomposes, the Fock space decomposes into irreducible representations, and F star does as well. And so it's just F sub L, where again, that L is essentially this number of particles, basically. The number of particles to the right of 0 minus the number of holes to the left of 0 is our L. And so FL has the highest weight vector, depending on whether it's positive or negative, but let's just say it's positive. You just create particles up until L. So you kind of, if 0 is here, then L is 3, and so we create 3 particles in order to get up to L. And that's the highest weight vector for this particular Fock space. And they're all isomorphic. They all just kind of, all you have to do is shift your 0 point left or right. But it does matter, because we do stay inside an FL when we're applying these group-like elements as operators. So let's talk about our states. This isn't quite going to be a basis as I've written it. You can easily modify it to make it a basis, but they're linearly independent. So let's take lambda a strict partition with L parts. And then all that I do is I take, all these parts are going to be positive, and so I just take the vacuum state and I add particles wherever there is a part of lambda. And that gives me something, because I've added L particles in FL. And similarly, I kind of do the opposite to get something in the dual. And you'll see that if you try to put these next to each other, to pair these up, these things kind of cancel. And then we get that, that the pairing of mu with lambda is 1 if the partitions are equal and 0 if they're not. And so essentially our goal is, what operators do we need to apply in the middle to move from one partition to the other partition, and what's the contribution of that? Okay, so more notation. There's a lot of notation here. I cut a lot of it actually. But so we have certain current operators, J sub n's. And again, these are part of our Lie algebra. So we create a particle, or we delete a particle at I, and we move it n spots down. So basically this thing says, wherever you have a particle, try to move it n spots left. If you can, good. If you can't, that part is killed, and so move on to the next particle. So it's all the different ways to move one particle n spaces left. And these current operators form a Heisenberg algebra. So this is this makes Fock space a representation of a Heisenberg algebra. And so we're going to create a Hamiltonian operator out of this. We basically have these parameters S sub n that we just multiply by the J sub n. So as far as the DRXC goes, we just, again, move the particle n spaces to the left, but we keep track of that S sub n, that contribution that we're getting from this. And we take a formal exponential of this Hamiltonian. So one way to think about it, if like just very roughly, is this just allows all different combinations of all different current operators in whatever order you want them to have. So given all of this, the thing that makes it all work is called the boson-fermion correspondence. And so what we do, these BKs that we're acting on the bosonic Fock space are just this scaling of these current operators, these JKs. They're the things that we put inside the Hamiltonian. And we get an isomorphism of H modules. So if we, in other words, if we want to act by the BK in here, or we want to act by the BK out of here, it's the same thing. So we get sort of the polynomial that you build up by acting on the bosonic Fock space is the same polynomial that you get by seeing if we have, oh, so A should be an FL. That's why we're pairing it with L. But essentially, if you you have this element of Fock space, we apply the Hamiltonian operator to it, and then we pair it with something. We get sort of the same polynomial that we would get by building stuff up in bosonic Fock space. And in the case that our parameters are actually the power sum functions, this is the classical case, we get the Schur polynomial. And I should mention this row is just the usual row shift, where everything is going to be row shifted here because we have to have strict partitions. But we get the skew Schur function in this way. So if we do this same procedure with something that is not the power sum functions, then we get other skew symmetric functions. Another fact I want to mention that I said in the intro is Wick's theorem. And Wick's theorem tells us, there are more general versions than this, but it essentially tells us how to calculate sort of something where you have a bunch of creation operators and a bunch of deletion operators. And there are n of each of them, and otherwise we're going to get 0 here. So what happens is you're able to take every single pair of one creation operator and one deletion operator and do those pairings on their own, and then just take a determinant. And so you can see perhaps that this is an analog of the Jacobi-Trudy formula if we look at it in this form. So if we have lambda paired with mu with e to the h, this is just the determinant of we create a particle at lambda sub b, and then we remove a particle at mu sub a. Okay, and we're going to name these functions in a bit. But I guess I don't need to hide it. These are analogs for the complete homogeneous symmetric functions. Okay, so what can we do when we have Hamiltonians? So this is, again, a lot of this stuff is from Lamb's paper. So let's give ourselves two different Hamiltonians. So here's kind of our positive Hamiltonian, which is the sum of the positive current operators and certain parameters. And for the power sum symmetric, if this is the power sum symmetric function, it's the sum of all x sub j to the k's. And so we're going to sort of generalize this by saying s sub k splits up into a sum of these things. And so if s sub k super j is x sub j to the kth power, then we have the power sums. But in general, this is not anything to any particular power. And so that's why we're more general than just Schur functions here. And so let's create another Hamiltonian exactly the same, except we're dealing with, oh, this should be, yeah, sorry about that. So something else exactly the same. These are different parameters because k is now negative. And so j sub k, we're now shifting particles to the right. And so what the Cauchy identity comes from is essentially what happens when we apply both of these operators in a row. And so we can kind of see this computationally very easily if you've followed all of the copious amounts of notation, that is. But let's have two polynomials. So these are kind of, so the g's and the f's, they're kind of like p's and q's, Macdonald p's and q's, Schur p's and q's. So if we have, so the G's basically pair lambda with mu this way with an H plus, and the F's pair them in the opposite way with an H minus. And so we want to find a Cauchy identity between these two polynomials, and we can. So we have the sum, and this is a skew version, so it's quite nice. So we have a sum over nu of G nu over lambda, F nu over lambda, and then we just write these in terms of Hamiltonians. And then it turns out that because we're summing over nu, it's kind of like for lattice models, there's similar stuff going on. But if we have a nu here and a nu here, we're summing over them, essentially it just means apply this operator, and then whatever you get here, apply this operator. And so that all compresses to this thing. And then we apply the commutation relation, and we get out by Baker-Campbell-Hausdorff, we get out this commutation relation here. This is very easy to calculate because we know the commutation relations of the current operators. And so we just do this commutation, and then we go backwards, and we just put it kind of, we just do these two steps in reverse, and then at the end, we have this factor, which often becomes a product, times this sum over the things where now the nus have switched from the G's to the F, and they're, or the lambda and mu have switched, and they've also kind of swapped that way. So this is kind of a skew Cauchy identity in several forms.
So on the left-hand side, the sum is infinite, but on the right-hand side, it's finite. Is that right?
Oh, that's a good question. Yeah, on the left-hand side, the sum is infinite.
I mean,
It's definitely the way it goes in the Schur
formula.
What, Ben?
I was just gonna, sorry, Dari, I was just gonna say in the Schur case, you know, that's certainly true, right? Because you have this requirement that the nu has to live within inside the partitions lambda and mu on the right-hand side.
Yeah, I think it's the e to the thing operator that makes up for the infinite, that makes things infinite, corresponding to this product 1 over 1 minus x I y j in the Schur case.
Yes, yes.
Okay, great. So that's our Cauchy identity. And so now we can talk about a Pieri rule, and we need to introduce yet more notation. So this is kind of this, I'm calling this eta sub k. This is our analog to the complete homogeneous symmetric function. And so essentially this is like, I have a particle in spot k, I want to move it k spots to the left. How can I do that? Like, what's the contribution if I apply the Hamiltonian there? And so we just call this eta sub k. And then we kind of, this thing, the kind of the operator analog of this is this operator u sub k. So if you know the kind of the formula for the, this is kind of the complete homogeneous symmetric function. These are kind of the power sum symmetric functions. So it's the same relationship between these operators as it is between those functions. And if we do this, then we get a Pieri rule that looks the same as if we were doing that. So the Pieri rule is just if I multiply by this eta sub k, I get a sum over mu of we apply u sub k to lambdas, and then we're doing g mu. Oh yeah, so this is on the bottom, this is rho, because as far as I can tell, these Pieri rule things do not work for skew functions, at least not in this generality. I haven't been able to figure it out, at least. But this is how Lamb says it as well. And so we can get another identity here, which is the Jacobi-Trudy formula. And this relies, again, on the fact that this is actual Fock space. So I should say that I've been a little bit sneaky for lack of time. And a lot of these things, they're Brockett pairings, and I told you what they were because they relate to this Fock space representation. but actually they relate to any representation. So the Cauchy and Pieri rules, if we have any Heisenberg algebra representation, we're doing a pairing like this, these things will hold. So the Jacobi treaty formula is not like that. That is specific to this particular representation. And so that just means that, like I said, we can apply Wick's theorem here. We get this determinant, and then this thing is a determinant of the eta sub k's. We have a row shift. That's why we don't have the plus b minus, or the plus a minus b thing. But essentially, this is, if these were the homogeneous symmetric functions, this would be the Jacobi treaty formula for Schur polynomials. So this, again, this comes right out of Wick's theorem. And finally, the branching rule is just my opportunity to introduce more notation. So remember, we have the S sub k's as sums of these S sub k to the j's. And what I'm going to do is I'm going to group that. So these are going to end up being the rows of our lattice model. So that's why I wanted to introduce it. So phi j is just the same thing as the Hamiltonian, except it's only the j part. It's not the whole thing. And so if we do that, we can write e to the h as a product of e to the phi 1, e to the phi 2, all the way up to e to the phi n, if we're dealing with n parameters here. And so the branching rule is just simple. You can just, like you would want to interpret these things, which if I had more notation we could do, but essentially you look at all the possible news that kind of fit in between any of these kind of pairs of operators. And so that gives us branching rules. Okay. So that's the background that I have. And so now we're going to talk about a question that now makes it fit for this seminar, which is how do we compare lattice models with Hamiltonian operators? And it's a very broad question potentially, because you could compare any sort of lattice model with Hamiltonian operators. And that's one of the interesting things about it. But specifically what we're going to do, we're going to start with the Six Vertex Model. And so this sort of thing was, I think there's some notes by Gustafsson that does this sort of thing with Schur polynomials. It might have been done before, although I hadn't seen that. And then Brubaker and Schultz did that for some of these functions that we're about to see. But so let's let S of lambda mod mu be a lattice model with n rows, m columns where m is big enough, and the 6 vertex model. So we have A1, A2, B1, B2, C1, and C2. Okay, and I'm not going to fix their Boltzmann weights yet. And in particular, I want lambda and mu to have the same number of parts because I'm going to do boundary conditions where we have all pluses down the sides. And mu has minuses wherever there are parts, and this has minuses wherever lambda has parts. And so what we imagine is that a minus sign is a particle. And so as we go up the rows, the particles move to the left as they're kind of, well, as they're going through the lattice model, but on the Hamiltonian side, it'll be as they're acted on by the current operators. So whenever we go through a row, the minus signs move, and we try to view that as the action of the Hamiltonian. So really our question is, when do there exist parameters, the parameters we've been looking at, such that this partition function corresponds to a Hamiltonian operator? And what I mean by that is essentially it equals the polynomial we get from the Hamiltonian operator. We're going to end up with a factor, a simple factor. But I also want this to work independent of lambda and mu. It would be too easy to just say, oh, for a given lambda and a given mu, can we find these things? We want these to be fixed and lambda and mu get to vary. And the answer, and this is something that I found kind of interesting, but so this is able to happen whenever the Boltzmann weights are free fermionic, and that's an if and only if. So if A1, A2 plus B1, B2 equals C1, C2, we have we're able to have a Hamiltonian such that it matches the lattice model. So this is what ends up being the parameter for the Hamiltonian. You can see this is in terms of the Boltzmann weights. And then if we do have the free fermion condition, we have the partition function being the Hamiltonian times this very simple factor. So I am interested by this because it seems almost kind of too nice to be true, because what we've shown then is that free fermionic lattice models correspond to Hamiltonians of free fermions. And so it's something that I've been looking a while for maybe a source for this, if it's been known perhaps for a long time. I haven't found anything, so I'm definitely interested to hear from anybody who kind of has seen a result like this, or knows the physics side well enough to sort of know what is known in that that area. But okay, so if there is anything that any thoughts anyone has, we can talk about it after. But I'll just sketch the proof of this fact, which is I think also kind of nice. So essentially what we do is we treat one particle systems, and we treat, essentially we start with one row partition functions. It's very easy to go from one row to many rows. So we treat one particle systems, and then we can just solve very directly, because there's always going to be one state and it's going to be very, very simple. And so you can prove that the result holds for these partitions, lambda and mu, precisely when these things are given by this expression. Okay, and again, this is you just solve for it. And then, so then, okay, what about multiple particles? Well, you do, again, the one row case first. And then what you do is you reduce to the one particle case via Wick's theorem. And it gives you a determinant. And the determinant involves those eta functions that I was talking about. And it turns out that that determinant equals the one row partition function precisely when the weights are free fermionic. It wasn't something that I was that we were anticipating happening. It was something that just kind of popped out of the equation. Okay, so there are a bunch of takeaways here. One takeaway is this. So this function, I think, is interesting for a couple of reasons. So I'm going to say why these functions are interesting. One is, okay, let's set x sub j equal to this, y sub j equal to the negative of that, and then this s sub kj simplifies to this function, which some of you may recognize as the supersymmetric analog of the power sum formula. So it means that we don't just have Schur functions as our partition functions. They're not just Schur functions, but they are this supersymmetric generalization of the power sum symmetric function. And so we have this this kind of correspondence here. When we have free fermionic Boltzmann weights, this corresponds to Hamiltonians of the above form, and this corresponds to supersymmetric Schur functions. So in other words, it proves the fact that also, like, it would not surprise me if this is in the literature, but it I guess seems from this that all partition functions with these boundary conditions with free fermionic Boltzmann weights are supersymmetric Schur functions, and vice versa. Brubaker and Schultz showed part of this. They took these supersymmetric Schur functions and showed that we get Hamiltonians that match with lattice models. And I've kind of done the reverse, where it turns out that all lattice models that have Hamiltonians, aka all free fermionic Boltzmann weights, have to be supersymmetric Schur functions. So that's takeaway one. Takeaway two, I'm not going to go into that much, but I did promise we were doing identities. So I just wanted to say that by the procedures that I did above, we obtained Cauchy, Pieri, and Jacobi Trudy identities for these functions. I believe these identities are all known for them, so I don't think any of those things are new, but we can have new proofs of these identities through this manner.
And Andy, when you say supersymmetric Schur functions, you mean supersymmetric Schur functions in possibly very ugly variables, right? Because you could set your Boltzmann weights to be anything that were free fermionic, and then you just make the variables equal to those ugly quotients of those Boltzmann weights, right?
Yeah, yeah. So
Okay.
I guess, I mean, yeah, so it's ugly if you look at it like this, I guess. I mean, it's not that ugly, right? It's just like xj is this, yj is this. It's just the
I don't know. I mean, the weights could look ugly. I mean, the weights
yeah,
could themselves
yeah.
be ugly, and then it'd be a Schur function in some supersymmetric Schur function in some horrible thing.
That's true. That's true.
Yeah.
I guess maybe then a way to say it would be if we wanted to parameterize free fermionic sets of Boltzmann weights, we could do that by the supersymmetric Schur functions. You can, yeah.
And real quick while we're on this, how do I get the superscript J parentheses from the A1, A2, B1, B2, etc.?
This just means like the row that it's in. Is that what you're asking?
Okay.
Like, yeah.
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 Thanks.
Okay, so then a third takeaway, which is a little bit of a wild card, I have to admit, but there's another reason that those functions are interesting, and they come in a version of the Edgeratoma theorem for Schur positivity. And so I thought I would just put this because it's a little bit mysterious to me, but the Edgeratoma theorem in this form says that let's take a homomorphism from the ring of symmetric functions to the real numbers. When is that Schur positive? Meaning for every Schur function, or equivalently every skew Schur function, we get a positive number from this thing. It turns out if we map the power sum symmetric functions to essentially these things, P1 slightly different, but essentially this formula where we have positive numbers here, then we get Schur positivity. And so one thing that means for us is that we can have some sort of positivity condition on our partition functions where if we have Boltzmann weights that are free fermionic and that have these quantities being positive, then we have a positive number. So they've got to be real in this case, or specialized to being real. Then they'll be positive numbers. And yeah, I found it interesting. The only reason that anything like this could work is because exactly the same function pops out. There's like a factor of k that kind of goes away, but this is exactly the function we had that we were specializing these things to. So all we need to do is make them positive. The other thing that I thought was interesting here is, so the one thing we don't use from Edgeratoma is this gamma. The P1 is allowed to go to some constant plus this, and if that constant's positive, the thing is positive. And so the kind of obvious analog would be delta, the sort of A1 plus A1 A2 plus B1 B2 plus minus C1 C2 divided by A times B or something. And we have free fermionics, so that's 0. But it wouldn't surprise me if perhaps by different methods you could get some sort of correspondence there where there was some relationship between this constant and your delta parameter. But that's very speculative. Okay, so that's what I just said. I want to say something else, which is we had very specific boundary conditions, which is plus on both sides. And I think for this sort of thing, that's the correct boundary conditions, because I think they're the most simple. And I think that's where the free fermionic gives us exactly supersymmetric Schur, as opposed to that with extra factors or extra stuff going on. So there are two ways we can deal with boundary conditions. Neither of them is amazing, but we can get a little bit with each of them. One is we can write sort of Hamiltonian-like operators for things with any boundary condition you want by just using creation and deletion operators judiciously. So for instance, let's have, I think Katie Weber mentioned this in her talk a few weeks ago, but we can have like this row transfer matrix. We have A is just pluses on the left and right, B has a plus on the left, minus on the right, C has a minus on the left, and D has 2 minuses. And if we have the situation that we're in where I got rid of the factor, but if this A matches the Hamiltonian, then can we get it so B, C, and D match Hamiltonian-like operators? Well, yeah, it's pretty easy. All you have to do is you sort of say that, say for B, we're going to pretend there's another vertex here. And so this minus is actually just going up here and around, and then we're going to divide off by that weight. So what we could say is we essentially have an extra C2 vertex, and then it gets us back to our boundary conditions that we were anticipating. So that gives us formulas like this. So we have a creation operator here, and we divide by C1. I guess that's a C1, sorry. Or we have a deletion operator here, we divide by C2, or in D, we do both of them. And so they're these kind of ghost vertices on the sides. Now, the only problem with this is these things don't commute very well. So if there were really nice commutation relations for these operators, this would be wonderful because we'd get all these great identities, but we don't. It's very hard to get anything nice with commutations because commuting these creation and deletion operators just like gives you other creation and deletion operators that don't simplify into operators like these. So as far as I can tell, this gives us an expression, but it doesn't give us a particularly useful expression. There is another approach, which is, say we have solid boundary conditions like our usual, say for like the Tokiyama models and stuff, and say we want to do this. Well, we're going to get an extra factor, but it's not so hard because what I'm going to do is I'm going to take this model and I'm just going to add on an extra block again to make sure when we combine them, we're going to get our correct pluses on the left and the right. And because there are n columns and n rows in this block, this is square. And so these things just have to go up here. And I believe Brubaker, Bump, and Friedberg proved that a block like this with free fermionic weights is going to have this partition function. So these are relatively easy to calculate. And so you just combine them into this thing, and we know that all the minuses have to go up here, and we have the partition function that we want plus times the partition function we don't want. And so that means if we have lambda be this thing with extra parts, then the original partition function that we wanted to compute is this Hamiltonian times this factor that we had divided by this factor that we just got. So this would be doable for any boundary conditions where it's all minuses or all pluses on either side. Okay, so the last thing I want to say is I'll talk a little bit about a generalization, which is Q Fock space and lattice models with charge. I think most of what I'm going to say comes from the paper by Brubaker, Buciumas, Bump, and Gustafsson that Dan talked about a couple of weeks ago. So I'm going to skip some of the background and just kind of try to fit it into this story a little bit. So we're going to deal, instead of with the regular Fock space, with the Kashiwara-Miwa-Stern Fock space associated to a quantum group. And so I only talked about the fermions. I didn't talk about the wedge relations, but essentially this U sub IM means there is a particle sitting at the IM spot, and there's a particle sitting at the IM minus 1 spot. And if there's a gap between these, there's a hole or multiple holes. And so this means eventually there are always going to be particles, essentially, if you go far enough left. And so what we have here, instead of the Clifford algebra relations, we get a sort of these wedge relations, where if UL is in front of UM, we want M to be in front because it's the larger particle. And so if they're equivalent mod n, you just swap them. and you get a negative sign, just like regular Fock space. And otherwise, you get this thing involving what's like often a Gauss sum, but in that paper, they sort of generalized it to any function mod n, and it could potentially be generalized a little further than this, but any function mod n such that G0 is equal to Q squared, so negative V, and GA times G negative A is equal to V. So as long as you have that function with these properties, we can have a Q Fock space with these sort of relations. And then we just have JK again is all of the ways of moving a particle K spots to the left. So this is, I think I wrote N instead of, oh, this should be, these should say KN. So here a JK moves you K times N spaces to the left. Essentially what we have is we have a representation that's N dimensional. And so if we want to go to like another power of Z sort of, we just skip over N spots. So that's why the JK is doing it. It's actually multiplying by some number, by some variable Z. So these should say NKs. And okay, so if you want a better exposition of that, you should go back and look at Dan's talk or his notes, because he said a lot more about it. But we're just going to consider a 6 vertex model with charge. And so these are our 6 vertices again, except now we have this charge component where essentially what it means is once a particle starts traveling, it can't just go one spot over, it has to go a multiple of N spots over. That's essentially what it is. And so we keep track of that by these charges. And so A is some number mod N. And so if we start with this, if we start with a C1, then we kind of go along with a bunch of B2s and A2s until we get A down to 0 again. And then we just pop up like here with a C2. Okay, so the big thing that we want to know again is, when do these lattice models with these boundary conditions equal a Hamiltonian or something like a Hamiltonian for Q Fock space? And we're going to, so one note is we're going to let V vary. So V is related to the parameter for the quantum group. And so in a given Q Fock space, it definitely does not vary. But I just think the result sounds nicer if you do let it vary and say, start from the lattice model side. The exception, though, it's an unfortunate exception, is that the Q Fock space becomes degenerate. It's certainly if V is equal to 0. And it's too bad because that would have been our favorite case. But the Q Fock space doesn't work if V is 0, or potentially if it's a root of unity. And so the answer, when does this lattice model have a Q Fock space, is when the Boltzmann weights satisfy these conditions. So we have essentially the free fermion condition at 0 charge. Then we have this condition saying essentially that V is not 0, but I'm trying to not talk about V, right? Because I'm looking at it from the lattice model side. And then the third condition is this sort of charge condition, which says this ratio A2 of 0 over B2 of 0 is the same as that's some fixed number that is sort of equal to this thing, whatever A is. So in a way, it's saying that this thing is constant regardless of A. And so I just to be kind of like cute about it, I want to call this the generalized free fermion condition, because it says when the Boltzmann weights have a Hamiltonian, and we have the free fermion condition for 0 charge as part of it, as part of these restrictions.
So
yeah.
So is C1 and C2 also evaluated at 0 there?
Yeah, but I don't think C2 can have any charge but 0.
Oh, okay. All right, that answers the rest of my question. Okay.
Okay, so then what are Hamiltonian parameters? Well, they're essentially the same thing. They look very similar. So we just do the same thing where we have something to the k and something, the -1 to the k minus 1. This is the same, something else to the k. It's just now these are slightly more complicated. They're products of these weights instead of just a simple quotient here. But essentially what this comes down to is the fact that once a particle starts traveling along a row, it has to go n spaces, or once a current operator acts on it, it moves n spaces, or n times k spaces. But we have these things, and they're kind of a similar thing. And oh, I forgot to fill in the factor. There's some simple factor involving these weights, but the partition function here is some simple factor times the Hamiltonian in that case. And I believe this is an if and only if, although I haven't quite shown that for sure. Especially because it's sometimes unclear what your assumption should be. And the thing that these authors showed is that we obtain the supersymmetric LLT polynomials from these partition functions, from these Hamiltonians. So this is we're all calling this the supersymmetric LLT polynomial. We can get this for any x and any y, where the x's are this, the y's are this. However, we have a problem, which is that we cannot have y equals 0 because of that second bullet point of conditions. We can't have y equals 0 because that would entail setting b equal to 0 essentially. But I believe that we can have any other parameters in here besides y equals 0. Now, the unfortunate thing is y equals 0 is exactly the LLT polynomial. So that's the one thing that we can't have. And that's kind of one of the things I think they were trying to do that too, and then I was trying to do it. And it's the one thing, at least without new methods, that you cannot get in this way. And so I'll just quickly summarize because I know we're about out of time, but identities, we can do Cauchy and Pieri identities for these things because Lamb's formalism just allows us to do that. Jacobi truly does not work because we're not dealing with the regular Fock space. We're dealing with the Q Fock space. It may be possible, I think Dan mentioned this in his talk, if someone could figure out a deletion operator, you may be able to create a sort of Wick's theorem for Q Fock space, and it might not be a determinant expression, but there could be something there. And then boundary conditions, we can do the first method where we kind of have these creation deletion operators. It's much harder to do that second method where we have the blocks that we're cutting off. But that's all I've got. So again, thank you for having me. I've really enjoyed being here.
Thank you so much. Let's thank Andy.